Somewhere in the constellation Aquarius, 650 light-years away, a dead star's remains are being taken apart, piece by piece, and fed back into the galaxy. For decades, astronomers watched this happen from a distance, through the bright, familiar glow of one of the most photographed objects in the night sky. What they couldn't see was the process actually happening at the edges. Then, almost by accident, a telescope that isn't even finished being built caught it in the act. This is the Helix Nebula, and what a team of astronomers just found in its faint outer halo is rewriting how we understand the final stage of a star's life, the moment its scattered remains truly become part of the universe again. Let's start with what the Helix Nebula actually is. Roughly 10,000 years ago, give or take, a sun-like star reached the end of its life, not with a supernova, not with violence, but with something closer to an exhale. As the star ran low on fuel, it became unstable and began shedding its outer layers into space in a series of winds and outflows. What was left behind at the center is a white dwarf, the hot, compact core of the star, still glowing faintly today. What was expelled outward became the nebula itself, an enormous shell of glowing gas that, from Earth, resembles a giant human eye, staring back at us. The Helix is one of the closest and most studied planetary nebulae in the sky. It's appeared in some of Hubble's most iconic images. The James Webb Space Telescope captured it in a level of detail we'd never seen before. By most measures, this object should have had very few remaining secrets. Every major telescope humanity has built has already pointed a lens at it. And yet, in November of 2025, a new instrument was being tested in Chile's Coquimbo region at a location called the El Sos Observatory. It's called MOTHRA, an acronym for Modular Optical Telephoto Hyperspectral Robotic Array, and yes, it's named after the giant fictional moth from Japanese monster movies. When finished, MOTHRA will consist of 1,140 telephoto camera lenses working together as a single enormous eye. At the time of this observation, it wasn't finished. Astronomers were simply using it for a calibration run, pointing it at a well-known target to check that the system worked properly. The Helix Nebula, being bright, nearby, and endlessly photographed, was the obvious choice. It was supposed to be routine, a test image, nothing more. Instead, the partially built telescope revealed something that had been sitting there, unnoticed, the entire time. Here's why MOTHRA could see what other telescopes missed. Large observatory telescopes use a single big mirror or lens to gather light, and that design, however powerful, comes with a side effect: internal diffraction. Light bouncing and scattering slightly inside the optical system in ways that can wash out extremely faint, extended structures. MOTHRA takes a completely different approach. Instead of one giant lens, it uses an array of smaller, high-end telephoto lenses working in concert. These lenses are much better at suppressing that internal diffraction, and that difference in design turned out to matter enormously, especially for the kind of target the team was about to stumble onto. When the researchers looked at the calibration data from the Helix Nebula's faint outer halo, far beyond the bright ring that shows up in typical images, they found something extraordinary. 22 glowing arcs of light, curved, like the wake in front of a boat, cutting through water. In astronomy, these are called bow shocks. They form when something moving fast slams into slower-moving material around it, compressing and heating that material until it glows. But these weren't the kind of bow shocks astronomers are used to seeing. Large-scale bow shocks, the kind typically observed around evolved stars, form on a grand scale, where an entire stellar wind pushes against the surrounding interstellar medium. What MOTHRA revealed was different. Smaller, more compact, each one tied to an individual clump of ejected stellar material, tearing through the thin gas of interstellar space and lighting up on contact. 22 of these tiny shockwaves scattered across the eastern side of the nebula, essentially invisible until now. So what exactly are we looking at? When that sun-like star shed its outer layers thousands of years ago, it didn't release a smooth, uniform cloud. It released clumps, fragments of gas and dust, metal-enriched material forged inside the star over its lifetime. Those fragments are now moving outward through space at somewhere between 35 and 45 kilometers per second. That's roughly 80 to 100,000 miles per hour, plowing into the thin interstellar medium that surrounds the nebula. Each collision compresses the surrounding gas into a glowing arc. 22 individual battles, still playing out, each one marking exactly where a piece of a dead star is currently colliding with the space around it. Here's where the data gets genuinely interesting. The researchers noticed that these bow shocks don't all look the same. Close to the central white dwarf, the arcs are large, thin, and sharply defined. Clean parabolic curves you could trace with a pencil, but the farther out you go from the star, the shocks become smaller, fuzzier, and increasingly fragmented, patchy structures that barely hold a recognizable shape. That transition isn't random. It's a timeline written directly into the gas. The team interprets this as a story of progressive destruction as each clump of stellar debris travels outward and interacts with the surrounding interstellar medium. It doesn't stay intact. Material gets stripped away from its surface, ablated, mixed into the diffuse gas flowing around it. The clump shrinks. It becomes porous. Eventually, it loses its identity entirely, dissolving into the same thin interstellar material that fills the space between every star in the galaxy. In other words, the outer, fuzzier shocks aren't a different kind of object. They're the same kind of clump, just further along in the process of being erased. By comparing the geometry of these shocks at different distances, the team was able to estimate how long that process actually takes. Their answer, roughly 10,000 years. That's how long a fragment of stellar debris stays coherent enough to produce a clean bow shock before it fully disperses and rejoins the ambient gas of the galaxy. 10,000 years might sound long on a human timescale. On a cosmic one, it's barely a blink. It's the length of time between a piece of a dead star being recognizable as debris and that same material becoming indistinguishable from the vast, quiet gas drifting between the stars. Why does this matter? beyond the Helix Nebula itself, because this process, the slow return of stellar material to interstellar space, is one of the most fundamental recycling systems in the galaxy. Every star that has ever died and shed its outer layers has contributed material back into the gas that eventually forms new stars, new planets, and yes, eventually, new life. Astronomers have understood the broad strokes of this cycle for a long time. What they've never been able to directly observe is the final handoff, the precise moment when identifiable stellar debris stops being debris and becomes part of the undifferentiated interstellar medium again. That handoff has always been a black box, too faint, too diffuse, too spread out for most instruments to resolve. MOTHRA, almost by accident, cracked it open, and there's a deeply personal footnote buried in this discovery. The Sun, 5 billion years or so from now, will go through essentially the same process the Helix Nebula's progenitor star went through. It will shed its outer layers, form its own planetary nebula, and scatter enriched material back into the galaxy. Whatever survives of Earth by that point will be caught up in a version of the exact same cycle captured in this data. The clumps, the bow shocks, the 10,000-year dissolution. It isn't just the Helix Nebula's story. It's a preview. The researchers are careful to note that this is one nebula observed under one set of conditions. The Helix is described as a fairly typical planetary nebula, which is precisely why the team expects to find similar fragment-driven bow shocks around other dying stars, once more telescopes look closely enough. Whether the 10,000-year dissolution timeline holds up elsewhere, whether it depends on the speed of the shocks or the density of the surrounding gas, remains an open question the same researchers are hoping to chase down next. For now, what stands out most about this discovery isn't just what was found. It's how. A brand new instrument, not yet finished being built, pointed at one of the most photographed objects in the sky, purely to check that its calibration was working, and in that single test image, it captured something no completed observatory had ever managed to resolve. Sometimes the biggest discoveries don't come from searching harder. They come from building an eye capable of finally seeing what was there all along. Beyond what you can see, but never beyond what you can understand. Subscribe, and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.